Okay, we're still working with direct proofs. In this video, I'm going to go over some common mistakes people make and some logical fallacies that are easy to make if you're not careful. So I'm going to be doing some things incorrectly in this, and then I will point out what I did that was incorrect and how to fix it. So let's start. Once again, we always want to remind ourselves how we do a direct proof. So I'm going to convert the statement, whatever statement, into a universal conditional statement. For all x in our domain, if p of x is true, then q of x is true. Right? If I wanted to say p of x is false, I would write it like that. So if I just say p of x, that means p of x is true. I want to start the proof by supposing x is a particular but arbitrarily chosen element of D, for which the hypothesis p of x is true. Again, that's supposing this first part here. Suppose x is in our domain and p of x is true. And then I want to conclude by demonstrating that q of x is true. Deduce or demonstrate q of x. Okay, so here's an example. If you subtract any odd integer from any even integer, is your answer always odd? Any odd integer from any even integer. Let's do a little example. Now, an example is not a proof, but it can help clarify our thoughts. So if I subtract 5 from 8, I'm going to get 3. That's odd. If I subtract 3 from 10, I'm going to get 7. That's odd. Again, these are not proofs, but it seems like this is a true statement. So let's see if we can prove it true. I'm going to, again, we sort of have statement part 1 is we want to write the statement as a universal conditional statement. So I'm going to say for all x and y that are integers, and I'm just going to pick, I'm going to say if x is even and y is odd, then x minus y is odd. Okay, so I've just written it a little bit more formally, using variables instead of saying just any odd integer and any even integer. I've given them names, x and y. And let's go through and try to do the proof. So, proof. So step 2, as always, I want to suppose the first part of my conditional statement. Right, then what's my goal? Well, my goal is going to be to show this last part of my universal conditional statement. Right, so this is step 2, and this is our goal. Well, let's do it. So, I missed something in writing my goal. We want to show that xy is odd, x minus y is odd. Maybe a better way of putting it is forgot to clarify step 2. Let's see if I can move our goal down a little bit. There we go. Okay, so if I want to suppose that x is any even integer and y is any odd integer, what's another way of saying that? So I'm going to say then x is even, so I'm going to let x equal 2k, and y is odd, is 2k plus 1 for some k in the integers. Oops, this is wrong. This is a really common mistake. Does anybody see what I did? It's a really common mistake. I am using the same variable k in both of these definitions. And what that means is I am unintentionally restricting x and y. Instead of letting y be any even integer, or x be any even integer, and y be any odd integer, I am restricting y to be exactly one more than x. So if x is 4, all right, let's say x is 4, which we know is even because it's 2 times 2, so we call k 2, then I'm restricting y, we call k 2, I'm restricting y to be 2k plus 1, which is 2 times 2 plus 1, which is 5. So while x can be any even integer, all of a sudden, because of the way I wrote this, y is constrained to be exactly one more than x. That's a problem. Okay, so this is a very common mistake people make, and that is to use the same variable to mean two different things. In this case, k, but it could be any variable to mean two different things. You cannot do this. Not allowed. If we have two independent elements, in this case x and y should be independent of one another, they need to have different variables. Right. So let's see. That's what I was afraid of. Okay, so we can let x equal 2k, but then y has to equal 2 times something else. So let's use q plus 1. And this becomes, instead of just k as an integer, q is also an integer. Right? We need two separate variables because x and y are not connected in this problem. They are allowed to be completely different from one another and do not have to be only one apart. So again, really common mistake. You want to watch out for that. If you made them the same, or if you use k for both of them, you would actually be able to prove that x minus y is always 1. Right? Because there's one apart. And one is odd, and so I've had many students in the past conclude that x minus y equals 1 and 1 is odd, so the statement is true. But that's limiting it. We need to stick with any even integer and any odd integer. Okay, so if we continue this proof now, we can say x minus y. Again, we cannot say it equals anything in particular. I can't say it equals odd. Okay, I apologize. My phone rang. So where was I? We want to show that x minus y is odd, but I can't just say x minus y equals 2k plus 1. Well, there's a mistake. Same variable. Can't do that. But we can't even say that x minus y equals 2l plus 1. Because, again, this is what we're trying to show. We're trying to show that x minus y is odd. We cannot start with the assumption that x minus y is odd. We can't do that. That's what we're trying to show. So, what I'm going to do is just start with x minus y and say, what do we know about x minus y? Well, we know that x is equal to 2 times k, some integer k, so I'm going to substitute. And I know that y is equal to 2q plus 1, so I'm going to substitute. Here's another common mistake. It's really easy if you leave off the parentheses to write that. Is that correct? No, that is not correct, right? We are subtracting this entire quantity, which is equivalent to saying 2k minus 2q minus 1, right? We have to subtract the entire quantity, not just the first term. So how can we do this first step? This is by substitution. How can we do our second step? Well, this is just by distribution. We're distributing the negative. This is one of the most common mistakes I see. And you guys have all had calculus if you're taking my class. So I really don't want to see problems with distributing a negative sign. Okay, if this had been a plus, this would be nice and easy. But it's not. It's a minus. And we cannot just say that 2 times some integer, right? We can't just say this is equal to 2k minus q minus 1, which is odd, right? Because this is not the definition of odd. Even if we know it's the same thing, because it is, it's not our definition, and we have to stick to our definitions. So I need to figure out a way to get a plus 1 here. All right, that is the definition of an odd number. It is, as we've seen here, it is 2q, or 2 times some integer, plus 1. So how can I force this to be a plus 1? Well, I can always add a 0 to an equation and it doesn't change it. Just like I can multiply something by 1 and it doesn't change it. I'm going to add 0, but I'm going to add 0 in a specific way. Let's say this is 2k minus 2q minus 2 plus 2 minus 1. So notice this is just 0. Right? So I'm allowed to do that by adding 0. And how does this help me? Well, I'm going to rewrite this as 2k minus 2q minus 2, and then I'm going to combine this last part. So this is plus 1. Now we can factor out a 2. This becomes k minus q minus 1 plus 1. This is by simplifying. And this is by factoring out of 2. Okay, I've run out of space. But notice our goal is we want to show that x minus y is odd. And so far, we've got it where x minus y is equal to 2 times k minus q minus 1 plus 1. So I'm going to go to the next page. And we have that x minus y equals 2 times k minus q minus 1 plus 1. This is from the last page. Now I can give a name to this quantity. So I'm going to say let z equal k minus q minus 1. So it's a new quantity. I need a new variable. What can we say about z? Well, it's the subtraction of integers. K and q are both integers, so is 1. So we can notice that z is an integer due to closure properties, or due to integer closure properties. Right? Which means x minus y, we can substitute that z in, is equal to 2z plus 1 by substitution. Where z is an integer, which is odd by definition. Because we've now met the definition that the value is 2 times some integer plus 1. And this is which was to be shown. Right, that was our goal over here. We wanted to show that x minus y is odd. We have just showed that x minus y is equal to 2z plus 1, where z is an integer, which is odd by definition. So that was what we were trying to show. Some of you may be wondering why I write my 7s and z's with a crosshatch. If you do a lot of mathematics, I've found that most people who do a lot of math end up doing this. It's because 7 and 1, some people write 1 like that, can look very similar. And z and 2 can look very similar. So I will always crosshatch. It's become second nature to me. I don't even think about it. I always crosshatch my 7 and my z. Not that that's important, but that's just the reasoning in case you were curious. Okay. So that was, this is an interesting proof just because it is so easy to screw up the little things. So again, I'm going to point out the things that are easy to screw up. It's easy to use the same variable here and here, and these need to be different. It's easy to forget to distribute the negative sign. It's also easy to forget that even if we know a number is odd, because minus 1 is going to give us the same result as a plus 1, it's going to be odd, we still have to stick to the definition. right? We have to stick to the formal definition. And finally, another really common thing that people tend to leave out, that you cannot leave out, is you must identify the fact, notice, I usually say notice, but you must in some way specify that our variable is an integer. Because just like that -1 versus +1, that is part of the definition. And we have to work with the definition that we're trying to demonstrate. Okay. Here is the formal write-up. I'm noticing here I used L instead of K. That's okay. Yeah, everything else should be the same. So you can pause this if you'd like to write it down. I also recommend before I start doing the proof that you pause the videos and try to do the proofs yourself. So, really important is when we're trying to prove an equality, we always break the problem into two parts. I typically do one for each side of the equal sign. So if I'm trying to prove that, 2a is equal to 1/2 4a, for example, I've got two parts to this equation, right? I tend to call this the left-hand side. I use the abbreviation LHS, and I tend to use the abbreviation right-hand side over here. It's then really important that you take one of the parts and try to simplify it. Not both parts. You cannot set the parts equal and simplify it. You are trying to prove that they are equal. You cannot assume it. All right, this is the mistake is known as assuming what you were trying to prove, and it makes your proof invalid. So don't do it. Really quick, I'm going to go through an example of this. If I want to prove this equality, the wrong way to do it, so do not do this, the wrong way would be to do something like 3a squared equals 3a 2 plus a minus 6a, and then try to simplify. So add 6a to both sides, so this becomes 3a squared plus 6a equals 3a 2 plus a, right? And then maybe we can simplify further. Multiply this out. This becomes 6a plus 3a squared. Hey, my sides are equal. I'm done. Ta-da. This is wrong. And you may be thinking, well, what does she know? Who is she to say that that's wrong? I've done this a million times in math, and it's always worked, and the teacher's always given me credit. This is a way of showing that the two things are equal. We can do that. If we show what that's meaning is we're saying we already know they're equal, let's illustrate how they are equal. If I am proving that they are equal, I cannot assume it. Right? So to prove it equal, I'm going to pick one side of the equation. So we want to sometimes I'll say we want to show it. I'm trying to figure out the best way of explaining this. Maybe a better word than show would be this is to illustrate, demonstrate. But you still want to be careful. And I'm going to show you examples why. We want to prove that 3a squared equals 3a times 2 plus a minus 6a. I'm going to call this the left-hand side and this the right-hand side. And we're going to see why it's so important to start with one and get to the other. So in this case, I tend to find the more complex side and start with that. Okay, so I'm going to start with 3a times 2 plus a minus 6a. And I'm going to say, well, that is equal to, if I distribute that 3a, I'm going to get 6a plus 3a squared minus 6a. Those cancel out. And this is 3a squared, which is the right-hand side of the equation. So we started with, the left-hand side. We started with the right-hand side, and we simplified it to look like the left-hand side. This is really important. So since we were able to do that, our proof is complete. Right? And let's see an example of why this is important. So in this problem, the only thing I changed is instead of this being a 6, now it's a 5. So let's try to do it the wrong way and see what happens. Okay, 3a squared. Let's actually, I'm going to add 5a to both sides. Okay, so the 5a moves over to the left-hand side. I can then distribute this. 6a plus 3a squared. What if we get rid of the 3a squared from both sides? We subtract it from both sides. Now we have that 5a equals 6a. If we divide both sides by a, we're going to get the 5 equals 6. So we've got some weird stuff going on here, right? So this is what can happen if what you're trying to prove is wrong, but you set it up and assume that it's correct, right? And work from there. You're going to end up with something really, really wonky. This is bad. The correct way to do this is, again, I'm going to start with one side of the equation. So I'm going to start with the more complicated side, just because I find that tends to be easier for me, but you can choose either side. And then I'm going to try to manipulate this to look like what we want. So 6a minus 5a is a, but this is not equal to 3a squared, which, if you recall, this was the right-hand side, and we've simplified the left-hand side. So these aren't equal. So what we've done is we've, in fact, shown that they are not equal, that this statement is not correct, which indeed it's not. Okay, here's another reason. I know this is a long video. I'm almost done. I'm going to demonstrate why one is correct and one is logically invalid. If this wasn't convincing enough that here we proved something that was incorrect, here I'm going to prove something else. If I'm trying to prove something that is incorrect, right? Sometimes I can show a proof that looks like it is correct. So I'm going to say I want to prove that 1 is equal to 0. So 1 is equal to 0. Again, this is the wrong way to do it. We all know that 1 is not equal to 0, but I'm starting with what I'm given. If 1 is equal to 0, then 0 is equal to 1. I can add these together, and I'm going to get that 1 plus 0 equals 0 plus 1, which another way of writing that is 1 equals 1. So look what happened. I proved something true. even though I started with something false. Right? If we recall from Module 2, if we start with false premises, the argument is unsound. So even though we prove something true here, this conclusion is logically invalid. Because, again, even though this is true and we know it's true, we started with something false. So you don't want to use an equality until you've proved that it's equal, or unless it's somehow given that it's equal. Right? Because here I was given it was equal, but this argument still doesn't work. So you always, always, always want to start with one hand side of the equation and get to the other. One final example, because I know this video is dragging on. If we assume we have two variables, a and b, where a equals b, again, we can do some wonky stuff. This is given. So that means that we can multiply both sides by a. And we get a squared equals ab. All right, I'm just multiplying both sides by a, like that. A squared, what can I do now? Okay, that's... So in fact, this is not quite correct. This is the part that's given. This is what happens when we multiply both sides by a. I can subtract anything from both sides. So I'm going to subtract b squared. And this is by subtracting b squared from both sides. I'm going to factor this. This becomes a plus b times a minus b. And over here I can factor b out. This is by factoring. I can cancel out the a minus b because it's on both sides. And now I have a plus b equals b. Okay, so we know that a equals b, so let's let a equal b equal 1. Then we have just proved that 1 plus 1 equals 1, or in other words, that 2 equals 1. Again, obviously not correct. Where was my mistake? This one's a little subtle. And this is why it's so important to be rigorous. The mistake is we canceled out a minus b. How do we do that? We said a plus b times a minus b equals b times a minus b. And we divided both sides by a minus b. Right, that's how we did it. But what is a minus b? If a equals b, then a minus b is 0. So we're dividing by 0. And that's not allowed. So we can't do this line. Actually, we can't do this line. Right? So this is yet another example of how if you're not very careful with each step, it's easy to make mistakes in a proof. So being very precise, being very particular, and being very careful are absolutely necessary when proving things. So the takeaway from this video, a couple of things. You always use different variables to represent different things. This is critical. You need to do it. Secondly, if you want to prove that two things are equal, do not start by assuming they're equal. Right? That's what you're trying to prove. You cannot assume it. Do not set both parts equal to one another and then simplify. Don't do it. Instead, start with one side of the equation and try to manipulate. Oh, you can't really see this, can you? That's a PDF error. Start with one side of the equation and try to manipulate it to look like the other side of the equation. Right? Very, very important, and I apologize this video was so long.